We'll now take an example of a relatively more difficult projectile motion question. So in this projectile motion question, you can see that you've launching the projectile as per normal. But unlike flat ground or just starting higher up, what's making this question relatively more complicated than many other projectile motion questions is the fact that you've got a sloping ground. So this green line here is the ground, basically. And that will make this question a little bit more complex than usual. But it is still actually very doable, which we'll basically take a look at doing now. So in our diagram here, we've got above the point O is the foot of the plane inclined at an angle alpha. Okay, so here's O, here's alpha. And a projectile is projected with speed v, very standard, from O at the angle elevation theta, here's theta, to the horizontal where theta is greater than a. Of course, if it's less than alpha, then you'll just go straight into the ground, which is not helpful. So you're going above the ground and then landing at some point. It strikes the inclined plane at P, which is the vertex of the parabolic path. Okay, so if it's the vertex of the parabolic path, that means this is the max height of the projectile motion. And it also means that it has no vertical velocity, and it will simply be horizontal as they're kind of kindly drawn in there. You may assume, as usual, that the parabolic path has these parametric equations. So just as always, read the question. They'll make it very clear what you can and can't assume for these questions. Sometimes they'll want you to prove it for part one. Here, they don't, so that's great. So you want to show that tan theta equals 2 tan alpha, and now show that the distance OP, which is the distance up the hill or the incline, is this expression here. Okay, so when you're looking at this question like this, you can see that there's no numbers, and they haven't really given you a whole lot of information. So the only way you can really do part one is to use the information that you do have, and you really then need to think about what information you do have that you can actually use, that is not just completely general, that applies to this particular case. So alpha is general, theta is general, v is general, you have some sort of curve, that's general. All of that's very general. But there is one and only really realistically one piece of information that is specific to our path, and that is here. It strikes the inclined plane at P, which is the vertex of the parabolic path. You can always strike the inclined plane, basically, but not always will it be at its max height. So we're going to need to basically have to use that piece of information that when it strikes here, it will be at the max height and will be horizontal to do this. We're going to have to use that somehow to do that. So let's write out what we know on our new page. So we know that x equals vt cosine theta, and we know y equals vt sine theta minus a half gt squared. We'll do a quick version of our diagram. So that's alpha there. And then you're going to have at some higher angle theta. And you're going to have some sort of trajectory based on that angle. And importantly, it's now horizontal at this point. And we're calling this capital P. So we should also recognize that we can get the equation of the line OP. So line OP has equation. I mean, it's a straight line going through the origin, so it's going to be some sort of y equals mx. But this m is equal to tan alpha, because remember, if this is alpha, then tan alpha is this over this, which is just well, m basically. So you can treat the equation of the line as basically y equals tan alpha x, and that will be useful to us later on. Now, it strikes it here so we might consider what point P is. So if OP is length R, so if we let OP equal capital R, then this will be at some capital R cosine theta, cosine alpha, sorry, and R sine alpha. So we know that there must be a point T. So at T equals capital T, X equals R cosine alpha, and Y must equal R sine alpha. So there is some particular T with that. And not only do we know that, but we also know that Y dot must equal 0 as well, because it's the maximum height at that point. So with that in mind, let's perhaps see what we can do at that particular point. So we don't know capital R, but we do know y equals vt sine theta minus a half gt squared. We do know that this time for max height, we'll get the time for max height. So y dot is this. So these are things that you do very frequently. It's going to be v sine theta minus gt. So we will let y dot equal 0. And if you solve for y dot equals 0 and solve for t, then t must equal v sine theta over g. And this t is our capital T. In other words, this is the time of max height. So when t equals v sine theta over g, then we must get our max height. So we can also know that this max height is going to equal so this r sine theta must equal the max height. And this r cos alpha must equal half of the range if it was level ground. Okay, because it's a parabola. And so you're cutting at the vertex. So the actual range here is just going to be half of that. So we know that half. Oh, I'm using a different R though. This is that R. So I can't use R again. So this is going to be half of the, can't use capital R for range, but it's half of the range, level ground range of level ground. So in other words, we also have the expression that r cos alpha must equal v squared sine 2 theta over g divided by 2. And we also have r sine alpha is equal to max height, which of course is v squared sine squared theta over 2g. So a few different relationships there. We're aiming for tan of theta equals 2 tan alpha. So if I've got this here, then that means, okay, so I'll write this on the next page. So I've got r cos alpha must equal v squared sine 2 theta over 2g, and r sine alpha equals v squared sine squared theta over 2g, then if you see these two simultaneous equations, then you can actually divide one by the other, 1 divided by 2. Or in other words, you can put them over each other, and that means you're going to get r sine alpha over r cos alpha equals, and I'll write it out like this, maybe that'll make it a little bit easier. So v squared sine squared alpha over 2g divided by v squared sine 2 theta over 2g, which is going to be v squared sine squared theta over 2g times 2g over v squared sine 2 theta. And you can see a lot of things cancel now. R's on the left cancel, v squareds cancel, 2g cancels. In other words, I'm going to get sine alpha over cos alpha equals sine squared theta over sine 2 theta, which of course can be written as tan alpha, because sine over cos is tan, equals sine theta times sine theta over 2 sine theta cos theta. And you can again see that sine thetas cancel, which means you'll get half times tan theta, and therefore 2 tan alpha equals tan theta as required. So that is part 1. Tan theta equals 2 tan alpha. So now they want you to find OP. So show OP, which we've designated as R ourselves, is equal to 2v squared sec alpha tan alpha over g, 1 plus 4 tan squared alpha. So we've already used this part. We've already used these two expressions. So you want to find this R. Now, if we can represent this R, we know this. If we can represent this R in terms of your X and your Y, then you should be fine. So if we can actually get if we can sub in X, if we can actually find this X horizontally, then all we need to do is then multiply by cos alpha, divide by cos alpha, and we'll get R, right? So X equals R cos alpha, so X divided by cos alpha is R. And if you look at what they want, they have a sec alpha in the numerator. So this is good. We just basically need to find X. All right, so what we're basically saying is, remember, X equals R cos alpha. So that means R must equal X divided by cos alpha equals X sec alpha. And we have a sec alpha here. So as long as I can show 2v squared tan alpha over g 1 plus tan squared alpha, 1 plus 4 tan squared alpha is X, then I'm good. So how do I do that? Well, I mean, there's a few different ways. So I'm basically just going to find the X. Now, if you look at this expression here, that might remind you of one of the sort of expressions that you've learned. So X must equal, we want to show X equals 2v squared tan alpha over g 1 plus 4 tan squared alpha. Now, there's probably a shortcut that I can kind of do there, but given it's worth 4 marks, let me leave that till a bit later. I don't think we can do that directly, but let's just think about if we could do it sort of more methodically and slowly. So to get X, as we said, we can sub t equals v sine theta over g into your formula of X equals v times t, already given, vt cos theta. So X must equal v times t times cos theta, which is v squared sine theta cos theta over g. Now, that's not wrong, but if you take a look what we need, we've got the v squared and the g, which is good, but everything else is in terms of alpha and tans. So let's get this in terms of tans first. So to get it in terms of tans, I'll divide by cos squared. So what that means then is I'm going to get v squared over g, which I'll happily keep. When I divide sine times cos divided by cos, that'll give me sine, and that will leave me with sine theta over cos theta in the numerator. You can probably see where this is going. The denominator has nothing, it's just 1 divided by cos squared, so that's just sec squared. And that's just going to be v squared over g times tan theta over, well, 1 plus tan squared theta. And if you think about what we proved earlier, in part 1, we've already proved that tan theta equals 2 tan alpha, which then, of course, means we can use that identity to then get v squared over g times 2 tan alpha, all over 1 plus 2 tan alpha all squared, which is 4 tan squared alpha, which then, of course, gives us what we want, 2v squared tan alpha over g 1 plus 4 tan squared alpha. So if you compare what I've got here in yellow to what I said up here, you can see that they match perfectly. We've shown x equals 2v squared tan alpha over g, 1 plus 4 tan squared alpha. So because the x is equal to that, and we recognize that x equals r cos alpha, then r must equal x divided by cos alpha, which is x sec alpha, which will then, of course, be 2v squared sec alpha tan alpha over g 1 plus 4 tan squared alpha. Now that is what they want, and we have completed the question using part 1, but they never actually said hence. So they haven't really forced us to use, well, I mean, we're going to need to use part 1 regardless of which way I do it. But let me just show you another way we could have approached this question. So remember, our aim in this question is to find r, and we're going to basically use very similar ideas. So r is equal to x sec alpha. We're going to need to use that, at least the way I'm doing it. But I'm basically just saying I'm going to find a different way to find this x. So remember, this is projectile motion. And this projectile motion is nothing special. It's just launch at v at angle theta. And so we have something called the Cartesian equation. So this is y equals tan alpha x. But this is, well, we can work out the Cartesian equation. It is not something you can generally use directly, and this question didn't give it to you. So to play it safe, you should work it out, but I'll leave that as an exercise. And also, I mean, we've done it many times before, but this is just going to be tan theta x minus g over 2v squared, 1 plus tan squared theta x squared. Now, you're trying to find x. So if I think of this as x, so this is the x to get to the max height, this is really just the maximum of the parabola. And I have the parabola. I have the equation. Because this is just the bx, and this here is my a. It's just a parabola with, I mean, a bit nastier looking a and a bit nastier looking b, but it's still a parabola, which is a quadratic, and I have the quadratic formula. I have the formula for the quadratic, which represents the parabola. So that means the maximum occurs from your year 10 work at x equals negative b over 2a, which is just, well, negative tan theta, all divided by 2 times a, which is negative g over 2v squared, 1 plus tan squared theta, which is negative tan theta divided by negative g over v squared 1 plus tan squared theta. Of course, doing that briefly, just keeping it all on the same page. We quickly find that that's negative tan theta times v squared over g, negative 1 plus tan squared theta, which of course means that you're just going to get v squared tan theta over g 1 plus tan squared theta. And so you've got v squared tan theta over g 1 plus tan squared theta, which you can see is what we had, v squared over g tan squared over 1 plus tan squared theta. So basically I got to this point over here, right here, using a different way. Instead of using sub the t of max height into x, I still got the x, and then the steps are the same. I will then convert the tan theta into tan alpha, and then I would again change from x to r. But two different ways, which will ultimately still give me the same answer. So basically, that's how you do the question.